Today we're going to talk about quantum mechanics. Yeah, that was quick.
See, David?
Which one is kind of alive or dead?
Is that the question? We'll get to it. Good. So, once again, I'm trying to address what I take to be fairly disparate backgrounds here. So just very crudely, well, here's the kind of experiment that people often appeal to in order to give people a flavor about what's initially strange about quantum mechanics. A particular version of such an experiment. Maybe not exactly the usual one. So, imagine that you have some kind of measuring device for X spins of electrons. Call it an X box. This is what's in this box is essentially a Stern-Gerlach magnet for people who are familiar with that. So you say feed electrons into this box, and the magnets are arranged so that if the X component of the spin of the electrons is up, they exit the box by this aperture, and if the X component of the spin of the electrons is down, they exit the box by that aperture. And we arrange things so that there are sort of reflecting walls for electrons set up at these two places. We have a box here which reunites the two beams. And here's an interesting fact. Suppose we feed in electrons whose Y spins are all up at this aperture. We measure their Y spins out here. It turns out their Y spins will all be up if the path lengths are carefully arranged to be the same, so on and so forth. But, and what I'm about to describe is a version of the Aronoff-Bohm effect. There's a certain sort of a box you could construct. So let me define a certain sort of a box as something I want to call a total of nothing box. Total of nothing, something satisfies the conditions of being a total of nothing box if it has the following properties. All of the observable features of any electron you feed into this box are preserved when the electron comes out the other side of the box, except, of course, its position in space by definition. Okay. But everything else, its momentum, its spin in all directions, its charge, its mass, whatever else you want. Okay. The conditions on something being a total of nothing box is that all of those measurable properties of an electron you feed into it come out the other side with identical values. So the box does, as it were, a total of nothing to the electron. Now, of course, one easy way of making such a box is just to make a box with nothing inside. Okay, that'll fulfill the conditions of being a total of nothing box. But of of course, there'll be many other ways to make such a box too. You can have a box which does all kinds of crazy stuff to the electron while it's in there, and as long as the box is, as it were, careful to exactly undo everything it did before it spits the electron out the other side, and as long as the electron gets spit out the other side at exactly the time it would have been if there were nothing in the box, then it counts as a total of nothing box. Everybody with me? And it goes without saying that a total of nothing box also by definition has no effect on any of the measurable properties of an electron that passes outside of it. Okay? And it was an amazing discovery of Aharonov and Bohm in the early 1950s. It was initially a theoretical discovery that it was derived from the quantum mechanical formalism, and it has since then been experimentally confirmed in enormous detail and under a wide variety of different circumstances. It's a fact that, so if we feed in an ensemble one at a time of electrons with a definite value of y spin into an apparatus like that, all of them will, would say y spin up into an apparatus like that, they'll all come out with y spin up at the other end. But it happens that if you say insert a total of nothing box, that is something that satisfies these two conditions in a total of nothing box. What I'm about to say is not true of any total of nothing box. The result is that there are boxes that you can construct that satisfy the conditions of being a total of nothing box. Okay? Such that if you insert them in this root, instead of 100% of the electrons coming out here with y spin up, 100% of them will come out with y spin down. Okay? And these boxes have been set up and explicitly empirically confirmed before we inserted them into this apparatus to have the feature that they have no effect on electrons that pass through them, and they have no effect on electrons that pass outside of them. Okay? But they have very definite effects, very vivid effects, very dramatic effects on, for example, the y spins of electrons that enter this apparatus here and leave it there in circumstances where you insert them here, or if you insert them here. If you insert two of them at the same time, the y spins will go back to y spin up here. If you insert any even number anywhere, you'll get all y spin up. If you insert any odd number anywhere, you'll get all y spin down. And this is one of many examples, of which the famous double slit experiment is supposed to be another example, and so on and so forth, of what, on the sort of traditional presentations of quantum mechanics, is supposed to be, well, the way this is understood on traditional presentations of quantum mechanics is as demonstrating that there must be situations that electrons can be in. Situations such as, for example, when you feed them into an apparatus like this, where there simply fails to be a fact about which of these two paths they're taking. Okay? Where questions, where in the way that philosophers used to talk, where somehow questions about which path this electron takes through the apparatus amounts to some kind of a categorical state. That is, asking which path this electron, asking whether the electron takes this path or this path through the apparatus is like asking, as Sidney Morgenbesser used to say, about the marital status of number 5, or about the weight in grams of Catholicism, or something like that. Okay. Such states are called, in traditional presentations of quantum mechanics, and also for mathematical reasons, which we'll get to in a few minutes, superpositions of situations in which the electron is taking this path and the electron is taking this path. Like I say, I'm caught between the impression of starting off at a wildly too elementary level here, or for some people doing the opposite. So everybody has seen these kinds of discussions before. Any questions about this kind of discussion? Any questions about how it is that people arrived at the kind of conclusion I'm describing from experiments like this or similar experiments like the double slit experiment? Anybody now? Yeah.
You mentioned that you have to tune the path lengths to be a certain way in order to get the results you described.
Yeah.
If you have a total of nothing box that itself is longer,
Yeah.
does that affect things?
Well, no, it depends. I mean, once again, this is, the result is certainly not, and it had better not be, that anything that counts as a total of nothing box will have this effect, okay? The result is that there are boxes that satisfy all the criteria. For example, inserting an empty box in this root won't have this effect, okay? But inserting a box with a constant non-zero electric potential inside it will have this effect, okay? So when you say if the total of nothing box was made longer, what effect would that have? You know, that depends on details of exactly what the design of the box is, okay? The crucial result is there exist boxes that one can specify that satisfy all the conditions of being, that satisfy these two conditions of being a total of nothing box, that if you insert them in here, will have this effect.
What I'm thinking of is that by definition, all the variables and classes of the box are invariant except the position.
Right.
So perhaps there's a link between how the positional information is what's being manipulated, and then
I'm not sure what you mean by saying the positional information is what's being manipulated.
No, maybe the point is simply that the effect of the total of nothing box is more or less the same as a change in the length of the path. And that is to say, it changes the phase relation.
Good, yes. Good. I see. Thank you, Shelley. Yes, that's right. The effect of the total of nothing box is the effect of the total of nothing box, at least on these statistics out here, is the same as a change in the length of one of the paths. But the change in the length of the path that the total of nothing box corresponds to isn't proportional to the length of the total of nothing box itself. It's proportional, in the example I gave, for example, to the value of the constant electric potential inside the box.
The details inside the box.
That's right.
Tell you something about the effective path length.
That's right.
That's right.
That's right. Good. Thank you, Shelley. I didn't understand the question. Yes.
So by total of nothing, you don't really mean nothing. Because if you apply an electric field,
No. In a region with constant electric potential, the electric field is zero.
Oh, constant electric.
Constant electric potential, not constant electric field. Okay? The electric field inside that box is zero. If there were a constant electric field in there, it wouldn't have these two properties at all. Yeah, it wouldn't be a total of nothing. It wouldn't be what I'm calling a total of nothing box at all. No, it's the electric potential inside the box that's constant. And since the field corresponds to the gradient of the potential, the field is zero. Everybody familiar with these kinds of discussions? Yes? Okay. I mean, I'm going to go through this very elementary stuff pretty fast. Another often cited, and rightly so, striking feature of quantum mechanics is that, and I'm going to say a little bit more about these when I come to say a few words about what the mathematical formulas but I just want to put these themes on the table. It's a feature of quantum mechanics, closely related to this feature of superposition, that quantum mechanics fails to respect a principle that was operative certainly in classical physics, and that's very deeply, intuitively hardwired again into our pre-theoretical attitudes toward the world, to the effect that you can tell a comprehensive story about what the world is doing at any particular instant by, as it were, conjoining stories about what each of its individual, what each of its most elementary physical constituents is doing, what each of its most elementary physical degrees of freedom are doing at that time. In quantum mechanics, that radically fails to be true. In quantum mechanics, there's a phenomenon of entanglement or of non-separability, okay? Where it's the case that there can be composite systems, that is, systems consisting of two smaller, separate subsystems that are in states, in so-called entangled states or non-separable states, in which there is nothing further to say about the state of either of the individual constituents of this system. That is, there are no definite physical properties of any definite physical observables of either of the subsystems separately that have determinate values, even though one can assign a complete state description to the pair of particles or to arbitrarily large collections of particles. Good. Yeah, it's becoming overwhelming that either you know all this stuff, in which case there's no point to it, or you're not going to get anything out of this. But we'll loop, let me mention one more thing, and then we'll loop back to all of this and talk about it in a little bit more detail. Third thing to have on the table, closely related to non-separability, is that quantum mechanics, modulo a certain assumption that I'll mention in a minute, quantum mechanics turns out to be demonstrably non-local. Okay, that is, first of all, the standard formalism itself turns out to include an instruction of the form that, under certain circumstances, if you do something over here, you ought to immediately change your description of the part of the world that's over here, completely independent of whether or not there's any conventional sort of physical interaction between this part of the world and that part of the world. And moreover, we have a proof from Bell that not only is that the case of the standard quantum mechanical formalism, but that that it's a straightforward mathematical impossibility for there to be any other formalism which gives rise to the same experimental predictions that quantum mechanics does, or even which gives rise to a very small subset of those predictions, a subset which as a matter of fact has already been well tested, okay, which could be local. Good. Can we put those three things on the table? And anybody want to interrupt with any questions at this point?
Can you give an example of this last one?
Yeah, we'll talk about that in a few minutes when I lay out the formalism in a tiny bit more detail. Yeah.
As far as I understand it, the standard view is that the Bell experiments give great evidence for non-locality, but it's always assuming several assumptions, and there's still loopholes that would allow a local
Well,
variable.
so it depends what you mean. There are several different categories of assumptions. First of all, there's an assumption and this will become crucial with respect to ways of understanding quantum mechanics like the many worlds interpretation, which I'll mention a little today, and which David Wallace is going to talk about in more detail tomorrow. There's an assumption in Bell's argument, an assumption which before you think of something like the many worlds interpretation seems so innocent and so obvious that you know, it seems crazy even to notice, okay? The assumption is that, that for every experiment you do, there's some determinate matter of fact. It's not deterministic, okay? It may be chancy, but after the experiment is done, there's some determinate fact of the matter about how the experiment came out, okay? That is, as a matter of fact, explicitly denied by the many worlds interpretation. And so the many worlds interpretation has an interestingly different relationship to this whole issue of locality than all the other interpretations of quantum mechanics do. But that's an assumption. And then there are, I take it the assumptions you're referring to are certain assumptions about, certain assumptions that we have to make that have to do with the fact that the detection devices we have for things like photons, which are the kinds of particles we do these experiments with, don't have perfect efficiency. Given that they don't have perfect efficiency, you can come up with all kinds of crazy conspiracy theories, such that you could have had a local account of what we see if there were conspiracies as to exactly which photons the detectors missed, and so on and so forth.
Or things
Yes.
like settings independence.
Yes, that's right. Yeah, there are those assumptions. I think it's fair to say that the experiments have now gotten good enough so that being worried about those scenarios is analogous to being worried under any other circumstances by radical skeptical doubts, like you're dreaming or there's a demon, you know, perpetrating a huge deceptive conspiracy against you by manipulating your experimental apparatus, so on and so forth. So, yes, logically speaking, those kinds of scenarios, you know, we don't know how to rule out those kinds of scenarios. I think that's sort of analogous to the fact that we don't know how to rule out general skeptical doubts, you know, general philosophical skeptical doubts. But anyway, you're absolutely right as a logical matter about it. Yes?
Just check, what's the status of like non-acceptability on hidden variable theories? I mean, maybe that this is something.
So we'll talk about this. We'll talk about this a few minutes down the road. All right, let me start to talk. I don't actually know why I started that way. Let me start to talk a tiny bit more concretely. Well, you know what? Let me maybe say two words about what's being violated here, which I guess I haven't done yet. So look, there's a very, very deep conviction that exposes itself in all of our ways of comporting ourselves towards the world. Okay? A conviction that's endorsed by every serious proposal for a fundamental physical theory prior to quantum mechanics. The original form of Newtonian gravitation was an interesting exception to this, but it was exactly because Newtonian gravitation didn't respect this that everybody, including Newton at the time, was convinced that it was a provisional theory that was going to be replaced by another one. Anyway, I'm sorry. So look, there's this intuition we have that things that happen here and now only directly affect things that are both spatially and temporally right next to them, okay? Immediately adjacent to them, okay? And in every situation where something happening here and now has an effect on something that's both spatially and temporally, or either spatially or temporally, distant from it, okay? Sufficiently close examination is going to expose that that's because there is a continuous and unbroken string of mediating causes and effects and causes and effects and causes and effects, stretching without a break from this thing here to whatever distant thing it is that has an effect on. Everybody with me? So that, for example, if somebody superficially thinks, say, that flipping a switch and turning on a light looks on the face of it like a violation of that, all you need to do is rip up the wall and find the wires connecting the switch and the light and do a deeper analysis of the physics of that situation and convince yourself that flipping a switch creates certain electric fields in the immediate vicinity of the switch, which accelerates certain electrons in the wire right next to the switch, which bump into other electrons further down the wire, and dot, 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 dot. And that's how the light ends up going on. And there's a very, very deep conviction, as I say, that we walk around with in the world, that that's what the world is like. Often, this intuition about locality is connected in the popular literature with special relativity. Special relativity certainly makes it easier to be clean about exactly what you mean by locality. But I take it the intuition of locality runs much, much deeper and is much, much older than any considerations having anything to do with the special theory of relativity. This is a really, really deep conviction that we walk around with about how the world works. And it's that conviction that's being violated by quantum mechanics. Okay? And not only by the standard quantum mechanical theory, but is necessarily going to be violated by any theory that reproduces the empirical predictions that quantum mechanics does, given this incredibly innocent-sounding assumption that there are facts of the matter about how experiments, about what the outcomes of experiments you do actually are. Yeah?
Might the deeper conviction be somehow connected to intuitive idea of cause and effect being spatial-temporally contiguous?
I mean, I would say it's the other way around. This idea about cause and effect is a symptom of this deeper conviction of locality. Yeah, I mean, once again, like I was saying about something else, about the probability distribution or something like that. This isn't just something that this isn't just an intuition that scientists have. This is an intuition that fish have, and bacteria have. Okay. This is a really, really deep intuition, that informs in ways way too numerous to count the way we make our way around in the world. Okay.
So the intuition is deeper than ideas about causation. The intuition drives.
Well, I don't know. Causation might be this kind of Jungian discussion of causation might be a different way of expressing the same intuition. I'm not sure I want to take a position on which one is deeper. They're getting it very much the same. They're getting it very much the same thing, and it's astonishing in a way that one can't exaggerate to imagine that. That in fact the world turns out not to respect it, okay? Under certain well-defined circumstances. Okay? So that the idea isn't, okay, that these two, that the effect of this on this is astonishingly fast or something like that. But let me say one more thing about locality. This intuition about locality carries with it a whole other set of expectations. That the capacity of this to influence this depends on things like how far apart they are in space, okay? Or what the physical conditions are in the spatio-temporal region in between these two events, okay? A denial of locality, such as we have in quantum mechanics, carries with it the idea that those sorts of considerations about the capacity of this to affect this are totally irrelevant, okay? Totally irrelevant, okay? So that there isn't, what you have in violations of locality are not situations where influence propagates particularly quickly or maybe even instantaneously between this and this. There are circumstances in which the very language of propagation is inappropriate, okay? The effect this has on this has absolutely nothing to do with anything that's going on in the spatiotemporal region in between them, okay? It's as if doing something like this somehow just is doing something to this. Another intuition that comes along with locality. If this affects this, it ought in principle to be possible, like with the lights, like with the switch and the light, by looking carefully enough in here, okay, to see stuff going on in here that you're going to be able to associate with some notion of the effect propagating from here to here, okay? That is completely gone in the kind of non-locality we're confronted with in quantum mechanics. Everybody with me here? Okay, yeah.
You said something I didn't quite hear or understand about an assumption that there's a fact of the matter about the result of an experiment.
Yeah.
I don't see how that is. Why isn't there a fact of the matter about the experiments that show the entanglement?
Yeah, no. I mean, the only I mean, this is just this is evidence of how innocent the assumption is. It's going to turn out to be the case on one way of trying to confront the measurement problem in quantum mechanics, the many worlds interpretation. That when you do an experiment, there simply is not any unique fact of the matter about how that experiment comes out. That is, an experiment typically has a bunch of different results in different worlds, okay? The world splits. There's one world in which the experiment came out this way. There's another world in which the experiment came out that way. There is no unique determinate fact of the matter, even once the experiment is done, about how it came out, okay? The arguments for Bell's theorem, okay, the arguments for non-locality in quantum mechanics, take it for granted that that's not the case. Take it for granted that there is a perfectly determinate fact of the matter once the experiment is done about how it came out. Tim?
So this is just a comment. I doubt that we'll get into this. Everything you said is perfectly correct, and it means that you can't appeal to the Bell argument.
Say it again.
Everything you said is correct, so you couldn't appeal to the Bell argument to argue many worlds have to be non-local.
Right.
It doesn't follow that it is.
No, of course it doesn't follow that it
There
is.
would have to be a longer discussion.
That's correct.
About whether, nonetheless, there is a kind of non-locality.
That's absolutely correct. Probably you and I have slightly different intuitions about how that discussion.
I think it's a subtle question.
I think it's a subtle question too. But anyway, that's right. The Bell argument can't be marshaled to show that it's non-local, because Bell's argument certainly is taking it for granted that once the experiments are done, there's a unique fact of the matter about how they came out. Yeah.
So what's the importance of having a discussion about locality and non-locality? I mean, it seems to me like it's not so clear even what we mean by locality. We go from one theory to the next theory to the next theory.
No, well, so let's see. If that's the case, then I've done a bad job. That is, I was trying just now to tell a story, a relatively theory-independent story, about what locality means. Okay.
It's just an intuition.
Yeah, it's an intuition with a content. Okay, one can say what the content of the intuition is, and one can ask whether this intuition turns out to be true or false of the world.
And there are philosophical implications too. I mean, there's a position called humanism, right? Where this is radical separability thesis, and something like this is gonna.
Yeah, I'm not sure. Of course, we can quibble about. You're absolutely right about that, as Hume put it. It seems to me a big chunk of what's important about his intuition can be separated from that. But
But for Lewis's humanism,
yeah, for Lewis's, I mean, Lewis certainly was taking something like that for granted. It's not clear to me, you know, Barry can answer this better than me. I bet if Lewis had lived a little longer, we could have talked him out of that part of it. Yeah, David.
I mean, just picking up a little bit on Casey's point, I guess this is one place in which you can mention special relativity being secondary, but where it comes into play. Because if we just had the kind of intuition that's going on here, we could say, well, you know, sure, fish had this intuition, but fish didn't do experiments with entangled systems.
Sure.
So it's just an intuition which is false. But then, and you can find out further. But then there's another goal that you have to find, which is going to be that it's at least prima facie very difficult to see how a theory that involves this kind of instantaneous, unmediated action distance is
Right.
going to be something that will be compatible with the symmetries of relativity.
Sure. I mean, like Tim said, the discussion about the relationship between special relativity and many worlds is also maybe a subtler one than it appears.
Yeah, no, absolutely. But I'm putting many worlds aside.
Right. Good. Yes, that's true. I mean, this is a question of what it is that one finds chiefly or most intellectually exciting about this. Well, I think what you said just now about special relativity is, of course, absolutely right. But what seems to me, you know, enormously earth-shaking about this discovery is that it puts at risk, or more than that, it shows to be false, intuitions we had about the way the world works that are so much older than special relativity, to which our cognitive commitments are so much deeper than they are to anything like special relativity. Or that's the way it seems to me. But of course what you're saying about special relativity is quite true. Yeah?
Even in the many worlds interpretation, it seems to me that there still could be a fact of the matter about the outcome of an experiment in our branch. So
Yeah. But that's not going to be enough to prove what Bell wants to prove.
There's no fact of the matter about beforehand of which of the branches is our branch.
Right. That's right.
And actually, one way to kind of like help for that, one thing you could take from this is if you branch relativize, it'll tell you that any global notion of branching in average is going to require some violation of covariance to send it up.
Right.
So the minimal way you read maths is the branching is going on globally. You've got a local branching on one side, a local branching on the other side. But if you try to do that globally, then you would get this effect. If you look at some of the earlier popular glosses of this, like the Wicks, then you find do talk about any measurement only here instantaneously equals the branch relate the inverse, and that's because they were thinking about a global nation of branching.
Right. Yes.
Is this only true at the microscopic level, or would it affect the Pope's coin flips?
I mean, it's you know, the effect of this can certainly be made manifest at the macroscopic level. Otherwise, we wouldn't have experimental access to these phenomena. But it's because of the way macroscopic objects interact with their environments and so on and so forth. It's extraordinarily difficult to sustain these kinds of non-local connections between macroscopic objects. In principle, it's possible. In practice, it's more or less out of the question with anything like currently available techniques.
Yeah, but David, it's still the case that these effects can't be used for any useful purpose.
That's
like
also
communication.
True. They can't be used to communicate information. Let me talk about. Let me back up and put a little bit of the formalism on the table, and then we'll be in more of a position to go into these kinds of questions. So look.
Can I ask a question about non-locality?
Yeah.
Will this be a problem for quantum field theory?
No. Well, I mean, yes. Let's see. I don't know what you mean. If the question is, does quantum field theory display the same kind of non-locality? The answer is yes. a question that's often asked is, but gee, there are all these proofs that quantum field theory is local. Those are, we'll get to this. We'll be in a position to say this more clearly in just a second. But the short thing to say about that is the quantum field theory that's being referred to when people say quantum field theory is local is a quantum field theory that doesn't include an account of how it is that measurements end up having outcomes. Okay. Once you add whatever it is you're going to add to quantum field theory in order to make it the case that measurements have outcomes, we have a proof from Bell that you're going to be sitting with something non-local, modulo these issues about the many worlds.
And it's more than that, David, though. When people say, and they have a precise meaning for it, quantum field theory is local, local doesn't mean, local is not meant in the sense that David has defined here. It's related, but not the same notion.
That's true. Well,
local commutativity of local observables at space-like separation may sound like the same locality we're talking about. I mean, think about it. It's not at all.
I mean, so we could and probably shouldn't have a longer discussion about this, and maybe I'm not sure I understand what you're saying.
I understand what you're saying.
Okay.
Normally, what they mean is just no signal. I mean, you're going to say that's fine.
No.
What do you mean by locality?
No, but no. It seems to me one could say they mean something stronger than that.
Oh, you think they mean something stronger? Just commutate with space-like separation?
No, they mean something like the Hamiltonian. They mean something like what you mean by saying in the first quantized non-relativistic case that the Hamiltonian is local. Okay. They mean something about the structure of the dynamical interactions. They mean something stronger than just no signal.
Even if that's what they mean, it still wouldn't. It is that very kind of theory to which Bell's argument does apply. So
no, I agree. But I mean, it's stronger than no signaling. It's something distinct from no signaling.
He mentioned quantum field theory, and that's because in quantum field theory there's an explicit basic assumption of local commutativity or local causality, which has precise mathematical meaning, and that precise mathematical meaning does not in any way imply locality in the sense that you have in mind.
In the sense that I have, you mean in the sense of sort of dynamical interaction?
No, what you were describing.
Oh, no, I agree.
But that's what he's asking about.
Okay. Okay. This is right. It was silly of me to dive into this discussion. Right. I don't think we're disagreeing.
We're not disagreeing.
Right. But maybe we'll be able to talk about this a little more. And once a little bit of the formalism is on the table. So let me tell you a little bit about the standard formalism. There are 5 things you ought to know about it. 1, in quantum mechanics, in the standard quantum mechanical formalism, you represent the states of physical systems by vectors, or more properly by rays, in a Hilbert space, okay, in a vector space, or equivalently by things like wave functions. The observable properties of physical systems, the measurable properties of physical systems, are represented by Hermitian operators on that vector space. Operators with real eigenvalues on that vector space. And in particular, the circumstances under which you say there is a fact that the states for which there is some particular fact of the matter about the value of a certain observable property are those states which happen, those state vectors which happen to be eigenvectors of the Hermitian operator associated with that observable property. Okay, so that, for example, there's an operator associated with position, okay, for a particle. The states which, the state vectors which are eigenvectors of the position operator with eigenvalues, say 5, are those states that represent the particle having a determinate location, and in particular the location 5, say along the x-axis. Yes?
Even if you're in an eigenvector state, then you still have to project onto that eigenvector.
Projecting from an eigenvector onto that eigenvector is doing nothing, is multiplying by 1.
Corresponds to the measurement of the apartment surface.
I'm not sure I understand what you're saying.
I mean, you have a vector that's just walking around, and it doesn't really care if it's in an eigenstate or not until you project.
No, but when it's walking around, as you put it, sometimes it will be in eigenstates of that operator, other times it won't. At those times, we're not yet talking about making measurements, okay? We're just talking about reading off observable properties from whatever the state happens to be at that instant, okay? And the rule for doing that, the so-called eigenstate-eigenvalue link, okay, is that if the state happens to be in an eigenvector, if the state happens to be an eigenstate of the relevant operator, then and only then is there a fact of the matter about the value of that observable property, and what its value is given by the associated eigenvalue. Okay? There's going to be more to say about what happens when you actually do a measurement. That's not what we're talking about at the moment. Okay? Good. Any questions? Third thing you need to know. This is where most of the physics is the dynamics, okay? That takes as inputs these vectors and tells you how to evolve them over time, given certain, external forces and conditions that the system may be subject to. And what it's going to be terribly important for us to know about the dynamics, and all it's really going to be terribly important for us to know about the dynamics for the purposes of setting up a measurement problem, which is what I'm heading towards here, is that the dynamics is linear. That is, that if I start out with a state, okay, that can be expressed as some linear combination, some superposition of two other states, alpha A plus beta B. And if it's the case that what the dynamics does to A over, say, 10 seconds is to evolve it into some other state, A prime, and what the dynamics does to B over the same 10 seconds under the same external conditions is evolve it into some other vector B prime. Then, and this is just what you mean by the linearity of the dynamics, what the dynamics is going to do to a superposition like this is evolve it into a superposition like this with the same coefficients. Everybody with me? Okay. Good. Two more things. We've given, and I take it this is what your question was about a minute ago. We've given a criterion for what it is for a certain state to be associated with a certain definite value of a certain observable property. Okay? The state is associated with a definite value of that observable property if and only if it's the case that that state happens to be an eigenstate of the operator associated with that property. And if it is an eigenstate of the operator associated with that property, the value that that property has in that state corresponds to the eigenvalue. Everybody with me? Good. But the theory is going to have to tell us, because our experience is you can walk up to any electron anytime you want and measure its position. Or you can walk up to any electron anytime you want and measure its momentum, and the measurement always has one outcome or another, okay? So the theory is going to have to tell us more than just that, okay? The theory is going to have to tell us in a more general way, okay? What happens if I walk up to an electron in an arbitrary state and measure its position. Okay? It's clear that if what we've said so far means anything at all, it had better be the case that if we walk up to an electron that happens to be in a position eigenstate when we walked up to it, okay, with eigenvalue 5, and measure its position, we're with certainty going to get the result 5. Okay? Otherwise, it's just not clear what we could have meant by saying that if it's that it has the property of its position being 5 under those circumstances. But what if the electron we walk up to isn't in any eigenstate of the position operator at all? Okay? There's going to need to be some rule telling us what to expect when we make a measurement, say, of the position of an electron like that. The rule telling us what to expect is the Born rule. It's probabilistic. It's chancy. This is the one and only place where chances enter into the standard formulation of quantum mechanics. And the rule, as everybody presumably knows, is that if, say, the state of the electron when we walk up to it is A, and we're wondering about the probability that a measurement of the electron's position would yield the number 5, what we do is take the square of the absolute value of the inner product between the vector representing the state that the particle was in before we walked up to it, and the vector associated with the particular outcome of the measurement whose probability we're interested in, take its absolute value, square it. That, according to the Born rule, is the probability that a measurement of the position on an electron whose state just before we carried out the measurement is A will yield the result x equals 5 is this number. Everybody with me? And one more thing. Presumably, once we've measured, say, the position of a certain electron to be 5, okay, then it's a fact, at least for a short time after, before the dynamics has had a chance to intervene and start to mix things up again. Immediately after that, presumably, the electron has a determinate position, and the value of that position is 5. Tim?
This is just a terminological review, but maybe it's worthwhile making.
Sure.
That, of course, in the story you're telling, which is the standard story, there's an operation you perform, but it is odd to call it a measurement.
Say a little more.
Because in the story you're telling, when you walked up the electron, it didn't have position 5.
Right. Oh, I see.
So the fact that you interacted with it in a way that, as it were, read out the outcome 5.
Yes.
Isn't in the normal sense a measurement.
Of course. Of course.
Interaction.
This is, if one were to defend
for it a position it didn't have. It's just terminologically, the word measurement, this is the point Bell makes.
Yeah.
Measurement carries all of this weight with it that is not only inappropriate, it is explicitly inappropriate for your service.
Yes. Maybe let's put it a little more carefully as follows. If you walk up to this electron and carry out those actions, which used to be called making a measurement of the position of the electron, that's what will happen. Okay. Good. Once that's done, on the other hand, we take it to be the case that at least immediately afterwards, before the dynamics, like I say, has a chance to come in and start to mess things up again, we take it to be the case that immediately afterwards, what we're dealing with is an electron about which there is a fact of the matter about its position, and the fact is that its position is 5, if this is how the experiment came out. Moreover, this can be, as it were, explicitly experimentally confirmed. That is, if we carry out a measurement of the position of the electron and find its value to be 5, and immediately after repeat the position measurement again, we'll find that with certainty, okay, modulo whatever chance the dynamics has had to interfere in the meantime, the result of the second experiment will be 5 as well. Okay? So that immediately after carrying out such a measurement, if it has this result, the state in which the electron gets left is apparently this particular eigenstate of the position operator. Okay? The one where the electron has location 5. So we've now learned something about how these so-called measurement processes affect the state of the electron. The electron gets, no matter what state we started out in, if this is how the position measurement comes out, the electron gets left in this particular eigenstate of the position operator. Okay? The eigenstate with eigenvalue 5. Everybody with me? Okay. And the important thing to note here is that this is that 2 claims have now been put on the table about how quantum states evolve in time. Okay. One statement that was put on the table, a statement which at least when we put it on the table, purported to be completely general, was the statement about the dynamics. Okay? The dynamics are expressed by differential equations of motion. There are a couple of other things I should have said about the dynamics besides its being linear. It's completely deterministic. Okay.
What would it mean for it to be linear but non-deterministic?
That's a good question. That's a good question. But it's worth emphasizing, even if it was logically implied by what I earlier said, that it's completely deterministic.
Probability distribution over states of time t plus 1 would be linear in states.
Say it again.
The probability distribution over possible states of time t plus 1 would be linear in states of time t.
Right. Good. That's true. Anyway, it's both linear and deterministic. And so, right on the face of it, there's a funny kind of tension between the claim that the dynamics is a completely general account of how states of quantum mechanical systems evolve in time, and this more specific claim about what must happen what must happen to the state when you make a measurement if all of this is going to hang together in anything like a coherent way. Just to make that a little bit more explicit, for example, the thought would be that if the dynamics is completely general, and if we have reasons for believing some particular claim about what must happen in cases like this, the particular claim ought to amount to a special case of the dynamics, ought to be deducible by just applying the dynamics to that particular situation. And there seem to be a whole host of reasons that present themselves immediately for suspecting that that couldn't possibly be true. The most obvious of which, the way I've set things up here, is that the dynamics is completely deterministic, and the way the state evolves under these, quote, measurement circumstances is governed by the Born rule. That is, it's chancy. Everybody with me? And if you look into this a little bit more carefully, the situation gets worse. Okay? That is, let's explicitly solve for what the linear deterministic equations of motion would predict about what's going to happen in a measurement situation. So let's explicitly set up such a situation. Suppose we have some device with a pointer on it for measuring, actually instead of positions, it'll be better to do it with say spins, just because it's mathematically simpler, because spins have only spin measurements have only two possible outcomes. So we set up a device to measure, say, the x spin value of a particle that has definite y spin. What does it mean that we have a device, a properly functioning device, to measure the x spin of a certain particle? Well, presumably it means something like this. This device, we're going to take it for granted that the whole world is described by quantum mechanics here. Quantum mechanics is supposed to be, it presents itself as a proposal for a new fundamental universal theory of the world. So presumably there's some quantum state of the device, or some set of quantum states of the device, which we might refer to as its ready states. Okay? Those are the physical conditions in which the device is plugged in and properly calibrated and facing in the right direction, and in all other relevant respects, ready to do its job. Okay? So this is some state vector of the measuring device. Okay? We bring that into the appropriate kind of interaction with, say, an electron whose x spin is up. That's the state of the electron. And if everything is functioning properly, if we allow this system to evolve in accord with the dynamical equations of motion, what it means to say that this is a properly functioning measuring device, all it means to say that this is a properly functioning measuring device, is that this is going to end up in whatever physical state it is, which, according to the design of that measuring device, is the state that indicates that the x spin is up. So this is some other state of the device. Presumably this may be a state in which the pointer on the device is pointing in a particular direction, or a state in which a particular light on the device goes on, or something like that. And in the ideal case, it leaves the spin of the electron itself unaffected. Okay? And similarly, if the device starts out in its ready state and the x spin of the electron starts out down, then it's going to evolve into indicates that down for the measuring device, down for the electron. Okay? And the idea is these two jointly, okay, where these arrows represent evolution in accord with the dynamical equations of motion, these two jointly amount to a definition of what it is for this device to be a properly functioning device for measuring the x spins of electrons. Everybody with me? And now, it's trivial to show from linearity. Okay? And I guess this was first done by von Neumann in his book on the mathematical foundations of quantum mechanics from the early 1930s. It's trivial to show, it's trivial to parlay this into a demonstration of what's going to happen in the event that you confront this device not with an x spin up state or an x spin down state, but say with a y spin up state. Okay? The way you do the calculation is that you take advantage of the fact that that y spin up can be represented as a superposition of, say, x spin up and x spin down, so that y spin up can be written like this. Oops. Okay. So, all you do, so the problem we actually want to solve is the problem of what would happen if we start out with a ready state for an x-spin measuring device, okay, and confront it with a eigenstate of y. Well, this can just be rewritten, given this, as this times 1 over root 2 x spin up for the electron plus 1 over root 2 y, x spin down for the electron. Multiply through, that gives us ready for the measuring device 1 over root 2, ready for the measuring device x spin up for the electron plus 1 over root 2, ready for the measuring device x spin down for the electron. Good. And now we notice that that this is just this plus this. Okay? So now it follows trivially by linearity that what this is going to evolve into, what this is going to evolve into, deterministically, is 1 over root 2 indicates that up x plus 1 over root 2 indicates that down x down. Everybody with me? That is, well, let's sum up what we've learned here. First thing we've learned, the suspicion that the so-called collapse postulate, that is this claim that after one of these measurements of say, the x spin, what the system does is immediately gets snapped into some eigenstate of x spin, the one corresponding to the outcome of the measurement. Okay, that's the collapse postulate. So the first thing we're learning here is that these worries that the collapse postulate couldn't possibly be what follows from the dynamics have been fully borne out. Okay? The collapse postulate doesn't follow from the dynamics. What the dynamics predicts deterministically and with certainty is something completely different. Okay? What the dynamics predicts deterministically and with certainty is that what's going to happen when we perform this measurement, that is, when we allow one of these devices to interact in the appropriate way with an electron that starts out with a definite value of y spin, okay, is that we're going to end up in a situation where there is no fact of the matter, according to the standard way of thinking about what it means to be in a superposition, about the value of the x spin of the electron. And moreover, where there is no fact of the matter about, say, where the pointer on the measuring device is pointing. Everybody with me here? Yeah? And there's a worry about what we should think about that. Okay. So, it's definitely not the case that the collapse postulate is any kind of a special case of the dynamical evolution, or in any way, shape, or form derivable from the dynamical evolution. It's not. Those two claims about how the state evolves under those circumstances completely and flatly and explicitly contradict one another. Okay? So that attitude towards the relationship between these two things is now ruled out. What attitude should we adopt instead? Well, von Neumann famously, who I guess is the one who I don't know, I guess arguably is the person who was first in a fully vivid way aware of this, said, well, here's what I guess you ought to do. You ought to say that the truth of the matter is that there are two completely distinct things to say about how wave functions evolve in time. One of which applies when measurements aren't occurring, and the other of which applies when they do. Okay? So that the right thing to say about how the state of the world evolves is that when measurements aren't going on, everything evolves in accord with the Schrodinger equation, or whatever the relativistic generalization of the Schrodinger equation is. That is, everything evolves in accord with the linear dynamical equations of motion. And that when measurements are going on, the sovereignty of those equations of motion is temporarily suspended and replaced by the collapse postulate, and that as soon as the measurement is over, the sovereignty of the equations of motion is reinstated until the next measurement occurs. Okay? You know, and it goes without saying that the only appropriate reaction to this is, you can't be serious. First of all, you know, the thing just sounds preposterous. Second of all, even if we wanted to try to take it seriously, we're not being given a way to do so, because the thing that's distinguishing between those circumstances in which the dynamics applies and those circumstances in which the dynamics doesn't apply is this sort of vague, sloppy English word measurement. Okay? A word which, as Tim says, in addition to all this vagueness and sloppiness, under these circumstances doesn't even seem to be the right word to use, okay? But this reference to sort of walking up to the system with a certain kind of apparatus in your hand, or something like that, those are the circumstances under which the dynamical equations of motion fail to apply. Everybody with me here? Everybody, I have a feeling that everybody knows all this and that we could be going faster and saying more. I just don't know. But I'm taking it from the fact that I'm bringing up questions that maybe we could be talking at a much more advanced level. No? Yes? Any questions? Yeah? Okay. Okay. So, so then you get, you know, very briefly, some people say, well, that's just crazy. Not only is crazy, it doesn't mean anything, it's ill-defined, so on and so forth. But for the next 50 years or so, what you get by way of improving on it is if anything, even more preposterous. So you have proposals like Wigner's, that the thing that marks the boundary between the circumstances in which the dynamical equations of motion apply and the circumstances in which the collapse postulate applies isn't marked by the word measurement, but it's marked by the presence or absence of consciousness, and a whole bunch of other proposals that have to do with words like macroscopicness or indelibility of recording or reversibility versus irreversibility or subject versus object, all kinds of mishigas, as they say in Yiddish. And nothing even remotely, and it should go without saying, and I take it was implied by my tone of voice, that all of these other proposals represent no improvement at all over the original one. They suffer from exactly the same crippling problems as the original proposal does. And thinking along these lines more or less stays in a track like that until you get to the 1980s. and the work of Girardi and Rimini and Weber, who finally produce a sort of what's at least a serious scientific version. Whether it turns out to be true or not is maybe another matter. A serious scientific version of a collapse constant.
David, what about, well, you'll understand why I'm asking this.
I'm not going historically.
No, I'm not even talking, no, let me say.
There's another tradition of thinking about it. Okay.
What about decoherence?
Oh, yeah, maybe that's worth mentioning at this point. Good. Good. Damn, I shouldn't have erased this. Good question. So, here's another so, let's write down the measurement problem again. Okay? You have an X-spin measuring device in its ready state. Okay? You confront it with a particle that has a definite Y-spin. Okay? What the equations of motion unambiguously tell you is that, contrary to your actual laboratory experience, that measurement, there's no determinate fact of the matter, ever. That is, there is with certainty no determinate fact of the matter about how that experiment comes out. Okay? That is, the state you're going to end up with, according to the dynamical equations of motion, is a state like 1 over root 2 indicates that up for the X spin, up X for the electron, and let me do some space here, plus 1 over root 2 indicates that down for the X spin, down for the electron. Good. And you say, this is no good. Okay? This isn't what we find. What we find is, if anything, something that corresponds either to this or to this in exactly the way the collapse postulate tells us things are going to come. But not this superposition, in which on the standard way of thinking, there's just no fact of the matter about what happens. There's a long tradition of thinking in a way that comes up again and again and again in the literature, that maybe taking some account of what the rest of the world is doing all this time might help with the measurement problem. There are various versions of that. A simple version, which was taken care of very decisively in the 1950s by Wigner, was saying, well, maybe if you add the observer to the mix, okay? So analogously to the way you think of the measuring instrument, you imagine an observer that is the human operator of the measuring apparatus. There will be a notion of what it is to be a properly functioning observer that's analogous, for this case, to the notion we introduced about what it is to be a properly functioning measuring apparatus. An observer is somebody who gets into the brain state corresponding to believing that the X spin is up when the pointer on the measuring device says the X spin is up, and conversely, when the pointer on the measuring device says the X spin is down, so on and so forth. It was Wigner who pointed out in the 1950s that if you add this observer to the mix with the observer's ready state, okay, it's going to do you no good at all. Okay, it's just going to make things worse. You're going to end up with a state here where you've got something multiplying this that corresponds to the observer believing that up in the X direction, and the observer believing that down in the x direction here. And all that's happened here is that now, not only does there fail to be a fact about the x spin of the electron, not only does there fail to be a fact about where the about what the measuring device indicates about the x spin of the electron, there fails even to be a fact about what the observer believes about the x spin of this electron. So that you might say, if you wanted to talk flamboyantly, this conflicts with our experience not only on the level of sort of, fairly direct perception of macroscopic objects in the laboratory, it conflicts with our experience at the level of straightforward introspection, okay? That is, our experience is that at the end of these sorts of processes, we end up with a determinate belief about whether the x spin of the electron is up or down. And this precisely denies that, okay? Yeah?
This is not exactly on topic, but I realized there was a comment that might be useful here to connect up with some stuff said yesterday.
Good.
It's just, I understand it's an interruption, to kind of just make it.
Sure.
Which is, of course, if you're, maybe everybody's familiar with it. If you're not, and even if you are, you should.
Yeah, I'm getting the sinking feeling that everybody's familiar with all of this.
But you ought to think, so let me just make it, connect it up to what we said yesterday. You might say, how could physics have done this, right? How could this have gone on for so long? Because, it doesn't take very long to point out
that there's a problem, right?
In a completely compelling way.
Right.
How could physics have gone on for half a century or more?
Right.
And this not been at the front of every mind? What the hell is going on?
Right.
And one of the answers to that, I think, I'll make this as a historical thing, is connected to what we were talking about yesterday. Namely, you look at what David wrote there, and you say, well, but notice this, if I just square these coefficients, the 1 over root 2 and the 1 over root 2, so I get a half and a half, I now have, in the mathematical sense, a probability measure. Right?
Right.
In the sense we talked about it. It satisfies the mathematical conditions for a probability measure.
Good.
Okay, so I squared those things, I got a probability, so I have the probabilities of these two outcomes. What's the deal? Why is that a problem? And that has to be what was in people's minds that they thought, why is there really a problem?
A lot of things that are in some logical sense the equivalent of that. I don't know if it was literally.
It's just because we talked about it yesterday.
Yes.
I said, look, you have to understand there's this gap between having a measure that is in the mathematical sense a probability measure, and that measure fitting into the physics in the right way to be the probability for something.
Right. There's
a gap, right? That's not a mathematical gap. That's a gap in understanding the physics.
Right. Right.
And that simply that observation does nothing to solve this problem.
Right.
Right.
Right. Good. 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 Let me and let me finally, because this isn't exactly what Shelley meant when he asked about decoherence. But what he did mean, I think, connects up nicely with what you just said. So let's talk about that. Here's another thing you might add in, besides a conscious observer. Just note that in addition to these two objects, okay, there's presumably going to be a lot else going on in the world. There are air molecules hanging around. There's electromagnetic radiation. There's all kinds of stuff like that. Those things interact quite strongly with things like the position of the macroscopic pointer on the face of the measuring apparatus. So that it's plausible to imagine, it's more than plausible, it's clearly inevitable, okay, that just as the position of this pointer is going to be recorded in, say, the diligent observer's brain, okay, it's also going to be recorded in all sorts of features of, say, the electromagnetic radiation in the room, okay, recorded with incredible redundance, okay, very quickly. If you want to get an idea of with what level of redundance and how quickly, just reflect on the fact that, I walk into this room and make a measurement of, say, the electromagnetic field in the immediate vicinity of my retina, okay? A tiny patch of the electromagnetic field. And I can tell from that a hell of a lot about the conditions of the macroscopic objects in this room. And I can tell that by measuring the electromagnetic field here, and I can also tell it by measuring the electromagnetic field here, and I can also tell it by measuring the electromagnetic field here, so that the presence of each of you here has been recorded very quickly and with enormous redundancy. Many separate measurable features of something like the electromagnetic field in this room, okay? And the same would happen to the position of a pointer or something like that. So you say, look, start off this way with, and there's some state of the E and M field, okay? Good. Multiply that here by a state of the E and M field in which it is multiply with incredible redundancy and rapidity recorded that this thing is indicating up. So call that the E and M up field. And here we'll have a corresponding E and M down field. Everybody with me? And people pointed out, yeah.
Sorry, can you say again why this redundancy?
Yeah, well, once again, just think about the following fact. I stand here and I measure the electromagnetic field immediately in front of my retina. Okay? Indeed, I do a crude measurement of the electromagnetic field immediately in front of my retina. I can tell from that how many people there are in the room.
I see.
Okay? Stand over here. Make a measurement of the different part of the electromagnetic field that's now immediately in front of my retina. I can tell the same thing. I can even see what people's faces look like. It's amazing. Okay? It really is amazing. I remember a passage somewhere in Feynman where he says it's as if there's a cockroach floating on the water in the corner of a pool, okay? And by measuring by sensing how he's going up and down on the corner of the pool, he can tell exactly who's jumping in the pool and where they're swimming around and so on and so forth. It seems like an incredible calculation to be able to do. It seems amazing that all that information is in there. And he could tell that if you dropped him in this corner of the pool, and he could tell that if you dropped him in that corner of the pool. And this is exactly what's going on when I walk into a room and open my eyes, okay? What each of you look like is recorded in the electromagnetic field over here, and it's also recorded in the electromagnetic field over here, and it's also recorded in the electromagnetic field over here, and so on and so on and so on. Okay? Good. So all these guys point out stuff like this. And they say, look, consider just this part. Okay. The part we were considering before. Suppose that we had such fancy measuring instruments or something like that. So this 1 over root 2 this plus 1 over root 2 this is some definite state of the composite system consisting of the measuring device and the electron, and the measured electron, okay? Call that state A, okay? That's some definite state of that composite system. A, necessarily, because this is true of every vector in Hilbert space, A necessarily is an eigenstate of some set of operators, okay? Note that A is a state in which the measuring device and the electron are entangled with each other. It's non-separable between the measuring device and the electron. A, on the other hand, necessarily is an eigenstate of some complete set of observable properties of this system. Okay? And by measuring those observable properties, we could explicitly confirm that the state after this interaction, if we could measure them, they'd be very, very difficult to measure. okay? But if we could measure them, we could, by so doing, explicitly confirm that the state after the measurement is done is not either this or this, that is one of those predicted by the collapse postulate, but rather this superposition, okay? And this superposition has different values, okay, for certain observable properties of this system than either of these states do, okay? So that in principle, you could explicitly, experimentally confirm if the dynamics were true, that it was the dynamics that was giving you the correct results and not the collapse postulate, okay? But people pointed out, but look, this by itself is never a realistic representation of what's going on. There's always an electromagnetic field around, or air molecules around, or neutrinos around, or cosmic rays around, or something like that. The actual situation is going to look more like this, okay? Of course, on some super principled level, okay, even this state, call it A prime, okay, is an eigenstate of some complete set of operators whose existence you could explicitly confirm by measuring those operators. But the business of measuring those operators, which would involve keeping track of every microscopic detail of the electromagnetic field that's propagating outward in space every second with the velocity c, and so on and so forth, just seems like, once again, not in principle ruled out, but by any stretch of the imagination of any imaginable technology that's ever going to happen, hopeless. Everybody with me? Now, this is the part where the logic is a little hard to follow. Maybe Shelley and Tim can say it more evocatively. I take it that encouraged the following slip, okay? And such a slip was made easier by sort of positivist and verificationist ideas about what there are facts about that were current at the time, and so on and so forth. There was a slip from the observation that this kind of a state would be incredibly difficult to distinguish by any doable measurements from either this state or this state, okay? To the different statement that the fact that the dynamics produced this, okay, could be legitimately read as a claim that the dynamics produced either this or this, each with probability of half. Do you think that's the right way to say it?
I would put it a little bit differently. Suppose...
I mean, but before you say this, let's just be explicit that whatever it is that they end up saying, it's a terrible mistake.
Yes.
Okay?
But there is no unique it.
Let me quote Bell to begin to make the mistake clear, because as usual, Bell says it the right way.
Right.
The issue is, all of these states you're writing, certainly if you take the eigenstate, eigenvalue link as your interpretive key to read off what properties the system actually has.
Right.
Are states in which certainly the pointer isn't actually pointing in any direction.
Right.
Right. And so on. It's not eigenstates.
Right. That is even the full.
Right.
Right. That's right.
They're certainly not.
Yeah.
And
you haven't yet characterized what mistake they were.
Okay. And what Bell says is, look, what you want is a transition from and, where the states you have there are in some sense this and that,
right,
to or.
Right.
And what Bell characterizes as the mistake, and sort of the problem with Schrodinger's cat isn't can we measure interference between the live cat and the dead cat. The problem with Schrodinger's cat is we think at the end of the day, in an objective way, independently of us, the cat just either ends up alive and not dead, or dead and not alive. It's either this or that.
Right.
It's not, in some sense, this and that, or neither this nor that, or whatever you're going to say about it.
Right.
So the question is, how do we get from an and to an or?
Right.
Now, I think part of the mistake made about decoherence is, first of all, jump from talking about the individual cat, which is, of course, the individual cat and the individual experiment, we think individually ends up either alive or dead,
Right.
to a big ensemble of cats. Okay? And say, suppose we had a big ensemble of cats, half of which were actually alive and half of which were actually dead. Right? Those would, each individual cat unproblematically alive or dead. And suppose we had a big ensemble of cats, all of which are in this problematic state. Okay? If we use the standard predictive algorithm to make predictions about measurements on those two ensembles,
Right.
okay?
Right.
The observation is, it would be you couldn't find any experiment you could do that would give different predictable outcomes.
Right.
And then, very badly, they say, so, there's really no difference between those two descriptions.
Right.
And look, the one description's okay, right? The
Right.
one description has a lot of live cats and a lot of dead cats.
Right.
And if the two descriptions are kind of equivalent, then the other one's okay.
Well,
Now,
but
part of the problem with that argument is just run it the other way. If the principle is this equivalence
Right.
you're pointing out means they're the same, you say, but the one is completely problematic, so it's
Right.
just the other is completely,
Right.
it's just a bad argument logically.
Right. Right.
That's part of what happened,
Right.
of people thinking that by making these interference terms become small or practically unfindable or something,
Right.
they could solve the problem.
Right.
But
I mean, I
it
think-
just doesn't go anywhere towards
I just wanna make sure I'm not missing, that sounds like what I said.
I think you have to bring it on, I'm not sure, I didn't hear in what you were saying, I think it helps to think in terms of ensemble.
I see, okay.
And what you were talking in terms of ensemble.
Right,
Like, that's-
right. No, I
that's
wasn't
the
talking in
difference.
terms of ensembles.
Let me-
But at the end of the day, you need some move like, the difference between this and half this and half this is difficult to measure, therefore identify. Right,
Let
right.
me add to another word, if you
Yeah,
ask me.
yeah, yes, please.
Which of course is not going to make the argument any better, but it's
Right.
something you often hear.
Right,
Namely, look, people say, look, science is about observation.
right.
If you can't tell the difference between those two things, it's unscientific to say there is a difference.
Right.
What's the problem?
Right, I mean, that's
It's
why,
meaningless to
that's what I was referring to as the sort of verificationist
Yeah.
influence here, that was operating in the background. Right, right, right.
But let me just say, I mean, the principle Shelley gave, you may find quite reasonable. It's not as if accepting that principle would solve the problem.
You mean because of the
Because
symmetry
they're
that you're
not,
pointing?
until you've solved the measurement problem, they're not observationally identical. I mean, look,
Right.
suppose I have
Well,
an ensemble of half.
On some ways of solving the
the
measurement problem, they're never observational.
Exactly. If
Yeah.
I actually have an ensemble of
Right.
cats, half of which are alive and half of which are dead, and I go through this and I say, what will happen if I look?
Right,
The answer is half the time you'll see a live cat and half the time you'll see a dead cat.
Right.
And if I have an ensemble, all the cats are like this, and I say,
Right.
what will happen if I look? The answer is you'll never see
Right.
a live cat and you'll never see a dead cat, and
Right.
you'll never get into a state of observing anything.
right,
So to say that they're observationally equivalent is question making, right? They're only observationally equivalent if you've already solved the measurement problem.
right. Even that doesn't, I mean, for example, on a collapsed way of solving the measurement problem, they're never observationally equivalent. On, say, a Bonian way of solving the measurement problem.
Right, but those observational differences are so subtle.
Right.
If you take this attitude, you say, okay, but those observational differences
Right.
are never checked anyway,
Right.
why do we care about them?
Right. David?
Yeah, I mean, I'm not really disagreeing with any of this, but I'm not disagreeing with this confusion thing. I'm a little nervous about quite how it's being diagnosed. And I think part of my nervousness is if you buy something, if the way that you think you can set up quantum mechanics lights in something like the eigenstate eigenvalue link to your very starting point of formalizing the theory, then sure, it's manifesting things nuts.
Right.
But I think while you run into the eigenstate eigenvalue link as a kind of frequent thing that's mentioned in foundational philosophical discussions, it's playing basically no direct role in the using of quantum mechanics. And you can do cute things like look for the phrase in the archives of physical review and it turns up about 3 times. And I think what's kind of going on a lot of the time the way this gets used is just a kind of there's kind of incompleteness in the way physics is using quantum mechanics, which is kind of about interpreting the quantum state as a state of a physical system in circumstances where it looks like that's what you better be doing, and interpreting the quantum state as a probability distribution in circumstances where it looks like that's what you're going to be doing. And there's nothing inherently wrong about writing down half live cat plus dead cat and saying that's a probabilistic representation of a situation. It commits you to understanding what probability is in various ways, but it's unproblematic in all over physics. There is something, of course, incoherent and confused about just kind of transitioning between these two different readings of what's going on without telling a proper story about why you didn't do it. But I don't think it's that physics was operating with a consistent and clean interpretation of the quantum state via the eigenstate link, and they just made a catastrophic mistake and got it wrong in this case. I think physics was operating with a much more consistently confused take on how to read the quantum state, and this is trading on the incoherence.
This is a detailed historical question, which maybe I just don't know what to say about. But I mean, it isn't obvious that that a way to get a good read on whether they were using something equivalent to the eigenstate eigenvalue link is to look for occurrences of that word, of that locution in physics. That particular locution, I take it, was an invention of philosophers. That's never the way. I don't think that's a phrase that physicists ever use. But it does seem like a lot of the physicists who were discussing this question were pretty clear that they had commitments like that. I don't know.
Yeah, well,
I don't know. This is a historical question.
Yeah,
Maybe I'm wrong.
well, tell you what, I've heard an interesting thing to think about. I think a lot of the way the philosophy literature has read a lot of this relevant physics does write exactly that way. Maybe that's right, maybe it's not, but I think the move to read it that way, carrying out philosophy, might have written in something that isn't necessarily there, as part of the way this is standard certain physics. And there's an interesting question to go back and look at those things from slightly different perspective. I'm quite sure doing it won't cause you to result to the conclusion that it's all just fine, but it identifies the points of coherence slightly different.
Good.
For what it's worth, though, I mean, I think there's a lot of truth to what David is saying, from my experience in talking to people.
Good. Chris?
Just a philosophical point. I know Tim just made the point that even on the assumption that verificationism is true, you really don't need a substantive reply or response to the problem. Right. But I mean, just sort of inform folks who are doing physics, verificationism is hopeless, at least temporarily in philosophy. Right. It's just almost universally dismissed for well-known reasons by now. I mean, one, there's a knowability paradox. Two, it seems to be self-referentially absurd. So even if you thought the assumption was going to get you a substantive reply, it's not a good assumption to make.
Right, but it wouldn't anyway. I mean, what I was referring to as the influence of that was, and I agree with what Tim said, it's not anything like if you were to take that attitude, you'd see a way out of this problem. It's rather that at the level of slogans, you can identify the kind of mistake that you can make a sort of psychological connection between the kind of mistake that's being made here and various of the slogans very superficially interpreted of something like verificationism. Yeah.
Yeah, I'm not sure what the philosophical term is for, but I would argue that the purpose of science is to provide good explanations of the world. And if you have two explanations which make the same exact predictions, yes, you can't verify empirically which one is better, but
no. We don't have two things here that make the same prediction. That's not what's going on.
You were talking about a single world and a many worlds perspective. Sure.
No. Wait. No. Let's see. I'm lost here.
Essentially, when you were talking about actual ensembles.
Yeah.
And so the question is, do either of those provide a better explanation for reality, and maybe they both provide a terrible explanation for reality?
But all of them on the standard way of look. Once
here, let me just. When I said actual ensembles, I have nothing like many worlds in mind.
Right,
I just meant, you do the experiment 100 times.
right.
When you're lab, you got 100 cats.
Where do you get the cats?
Where do I get the cats?
From a cat store.
Alleviate some nerve
It's just that you just misunderstood what I was saying. I was making zero reference to many worlds.
Right.
I was just talking about doing experiments many times in succession in order to get empirical statistics.
Your ensemble was in one world.
Yeah,
Yeah,
that's all I was talking about. There was just a misunderstanding.
Yeah.
I didn't understand my comment.
right.
It might help us translation. Sometimes ensemble gets used in physics just to mean genuine infinity of systems. But you don't mean that. You just mean a
No,
whole
it's
bunch of
a selection of things.
Right.
If you statistics.
Right. Good. So from the 30s, I guess, through the 80s, I mean, there are all kinds of ways in which some of these traditions persist even today. But all that was going on, more or less, at least in this train of thought, there's a whole other train of thought that has to do with Bohmian mechanics and so on, which I'll talk about this afternoon. On this train of thought, all that's going on from the 30s up until the 80s is a whole bunch of crap about either preposterous proposals for where to draw the line between those situations in which the dynamics governs the evolution and those situations in which the collapse governs the evolution, like von Neumann's proposal, Wigner's proposal, macroscopicness, indelible recording, irreversibility, blah, 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 or various other strategies like this to sort of to try to convince the listener that the apparent tension between these two principles is somehow merely verbal, or if you look at it correctly, there's no real problem, or something like that. Okay? Now, there's a certain sense in which you might want to fit many worlds into that second kind of tradition, but I don't want to be talking about many worlds right now. I will a little bit later in the afternoon, as I said, Dave, and we'll much more tomorrow. But the kind of decoherence strategies for dismissing the problem just don't work for the reasons we've been through. So it seems astoundingly to have taken, what is it, 60, 70 years for people to say to themselves, this actually seems to be a genuine problem, and maybe we ought to think in a serious scientific way about what the hell to do about it. Okay. And it was in the early 80s that, for example, within the tradition I'm talking about now, there are other parallel traditions, which I'll talk about in the afternoon. People like Girardi, Rimini, and Weber tried to take that attitude towards this problem. And they produced a picture like this. So here's the rough idea. Here are the laws of the evolution. Let's start with a single particle system. Okay? Here are the laws of the evolution of the wave function of a single particle system. Single particle system, the wave function of a single particle system almost always evolves in accord with the Schrodinger equation in the non-relativistic case, or some relativistic generalization in the relativistic case. with the following exception. Every now and then, and the probability per unit time of this occurring is fixed by a new fundamental constant in this theory. Okay. Every now and then, as the wave function is minding its own business, evolving along in accord with the Schrodinger equation, for no reason at all, out of nowhere, as a matter of fundamental physical law, it suddenly gets multiplied. Well, let me give you a naive version, and then we'll make it a little more sophisticated in a minute. Every now and then, for no reason at all, out of nowhere, it suddenly gets multiplied by a position eigenstate, okay? By a wave function representing an eigenstate of position, okay? Moreover, the probability of its being multiplied by an eigenstate of position with eigenvalue 5 as opposed to eigenvalue 6 is fixed by the Born rule probability that if you were to have measured the position of the wave, of the particle in its state immediately before this multiplication, you would have found it at 5. Everybody understand what the rule is? Yeah? And then the wave function proceeds along as it did before. Okay? Good. Here's what's cute about this idea. Let me back up a few steps. I'm sorry. This morning's talk is extremely disorganized. Prior to writing down a specific proposal like this, Garrity, Ramini, and Weber had to ask themselves in a more, I mean, these are extremely straightforward questions. It's amazing that they weren't asked in a serious way before this. What they wanted out of such a theory. And I take it there were two desiderata that were important in their minds. One, whatever process they were going to add to the Schrodinger evolution had better have the feature that it leaves all of the good predictions of Schrodinger, all of the experimentally well-verified predictions of Schrodinger evolution in place. Okay? That is, whatever it is they're going to add had better cause only negligible modifications in the Schrodinger evolution of fairly well-isolated, very microscopic systems. Okay? Because for systems like that, we have extremely strong reasons to believe that the Schrodinger evolution is correct. Everybody with me? Okay. Second, they had to answer a question of the form, look, what's the goal of this contemplated modification of the Schrodinger equation? Well, the goal is that experiments should have determinate outcomes, okay? Or more generally, okay, that all of the predictions that the standard equations of motion make, and the weird predictions that they make about macroscopic observables are usually, although not always, associated, or most frequently associated with cases, measurement-like cases, where you manage somehow to couple the state of a macroscopic observable to the state of a microscopic observable. Okay? Anyway, you want measurements to have outcomes. What does that mean? You want measurements to have outcomes. You want measurements to have determinate outcomes. If we're going to build a genuine physical theory around this, we need some more concrete interpretation of what the demand, of what it amounts to demand that experiments have determinate outcomes. And GRW fasten on a particular interpretation of what that means, which is going to come up again and again in various other ways of solving the measurement problem. Okay. The particular concrete interpretation that they fasten on is it will suffice to do that if we can somehow guarantee that there are always, or almost always, determinate or almost determinate facts of the matter about the spatial positions of macroscopic material objects. Okay? Yes?
So, for the majority of fundamental constants, there seem to be like reasonably clear empirical means of determining their values.
Yeah.
So I worry that there isn't a similar strategy available here beyond picking the values so that it rules out macroscopic or embarrassing superpositions without affecting the...
Well, no, I don't understand. At the end of the day, you can, whatever value you pick, okay, yeah, so there's going to be...
So what kind of empirical...
Wait, there are two separate questions here. There are two separate questions which it seems like you're smushing together.
Okay.
One question is what kinds of motivations are there for making a particular guess about what those values are when you're constructing the theory in the first place?
So I'm happy.
Second question, once the theory is in place, what means are available for actually testing the values of those constants? Those are two separate questions, okay? Yes, there are certain motivations, and as you said, the motivations are fairly loose, okay? You want the collapses to be rare enough, okay, so that they don't disrupt the behaviors of microscopic, fairly well isolated physical systems, and you want them to be frequent enough so that they never allow macroscopic material bodies to be in superpositions of macroscopically distinct spatial locations for any reasonable amount of time. That provides a window into, which suggests a value for this fundamental constant, the rate of collapses per unit time. Once you propose such a value, there are all kinds of other experimental consequences that it has. For example, a process like this will violate conservation of energy. Okay? If you start out with a gas of elementary particles at very low temperature, okay, so that each of their wave functions will be dispersed throughout the container. It's totally thermally isolated. I'll get to you in just one second. It's totally thermally isolated. You leave it alone. You come back later, it'll be hotter. Okay? Because some of these collapses will have occurred. They will have made the energies of those particles uncertain. There's no place for those energies to go but up if the particles start out very cool. And the rate of heating is something that will be calculable from this. The rate of heating will depend on the rate of hitting, and so on and so forth. This is just one among an infinite number of potential examples. Once you pick a value for these constants, it's going to have all sorts of experimental consequences. You just need to be clever and figure out what they are. Okay? But the minute you pick a value for these constants, it's going to have all sorts of experimental consequences. And the thing to do is go out and test them. Sure. Yeah, Tim, sorry.
So I just want to say, look, we have a recent thing which is exactly the same methodological situation. So think about the value of the Higgs, right? The mass of the Higgs. Why think there was a Higgs in the first place? Why propose it in the first place? Well, because it did certain theoretical work that you might have done.
Right.
And you proposed it, you said, well, big range of masses it could have where it would do the appropriate work. And then you think hard, can I do an experiment or make an observation or whatever to narrow down the masses? And at a certain point they were worried, maybe you look, you don't find it. I'm just saying, methodologically, exactly the same situation.
I agree.
So it's not as if Girardi, Ramini, and Weber were doing anything that from a normal point of view of regular physics was at all odd.
I agree. Also, just to say some other things, more practical experiments, another effect of these, of the value of this constant, another thing that can happen when an electron, say, gets hit by one of these multiplying position eigenstates. Well, so let me go immediately, now that we're discussing this, to the slightly more sophisticated version.
But David, before you go on, let me say, with regard to that question, Girardi really was, in fact, not too happy about fact that there was so much arbitrariness in his choice.
But there's less now.
No, there's less now, but still,
Yeah.
he had the similar feeling in proposing the theory.
Yeah, but look,
So can I just get Tim's point?
Yeah, sure.
I think it may seem like not quite. There's one element difference. I mean, we didn't know where in parameter space the Higgs mass was going to turn up, but there was a region of the parameter space such that it didn't turn up anywhere in that region, then the simple Higgs model was just going to be ruled out completely. Now,
But that's sort of true here too.
Absolutely the same here.
Well,
Yeah.
That happens once every 35 minutes. I mean, that would still be empirically what we have.
Well, Roddy, I mean, I would look at Roddy's paper about narrowing stuff, and that's the question of, the question is here, and I'm sorry if this is gonna, what are we trying to achieve, okay? I mean, that was David's point. What do we want out of this theory? The attitude going in is that if there are collapses only every 35 minutes, that doesn't achieve what we wanted to achieve, right? It means that for whole 35-minute periods, there's no fact about what we're seeing or what we're doing.
That's true. I take it
and the view is that would not be an acceptable resolution of the problem we thought we had.
But I take it David's point is, granting all that, it's not clear what explicit empirically established fact that would constitute a violation.
Only if you say it's not an empirically established fact that I'm having experiences continuously over 35 minutes.
Wait, if it continuously, it's not going to get you. It takes finite amounts of time for the collapse.
But I mean, over 35
even
minutes,
if they're
I
very
have lots
small.
of different experiences.
Yeah, no, that's right.
If you say that's not empirically established,
wait.
I'm not quite sure what you mean by empirically established.
Let's be a little bit more careful. The thing that needs to be empirically established is the distinction between you're having had these experiences continuously over 35 minutes and you're remembering having had them at the end of that interval. Okay. One can have arguments about what the nature of the clear empirical distinction is between those.
We shouldn't get into this. I would just say, I think, in the only sense I understand empirically established, if it's not empirically established that I'm having many different experiences over 35 minutes.
Then you don't know what it is.
I honestly don't know what you mean by empirically established.
Okay. I see how to go on with this dialect, but let's not do it right now. Anyway, sorry.
Just to, this picks up a preferred basis in Hilbert space?
Sure.
Position space, right?
Absolutely.
Okay.
You got a problem with that?
Just checking. And again, just checking. So is the idea here that this induces a global instantaneous collapse? It's not local?
No, of course it's not local. No, it's radically non-local. It's radically non-local. Okay, I guess we'll pick this up when we come back. Let me just say, because people were getting too sophisticated too fast. Look, if the multiplying wave functions actually were delta functions like this, that'd be a really bad choice. Because in that case, the violations of conservation of energy involved in each of these collapse events would be literally infinite, okay? The minute one of these occurred, the chance would be one that the universe would explode, okay? And so there wouldn't be, and so lo and behold, there wouldn't be an outcome to your measurement after all, okay? So you don't want to do it that way, okay? You want to do something that's going to involve the introduction of a second fundamental constant. That is, the kind of thing you're going to want to do is make the shape of the multiplying wave function something like a Gaussian, or something much smoother. That it's exactly a Gaussian, I don't see any good argument for. But a Gaussian is what people often choose. You make it something smoother. That is, you notice, as you were saying, that there's another window of opportunity here. Okay, just as there's an opportunity to make the collapses rare enough so that they don't disturb the behaviors of isolated microscopic systems, but frequent enough so that they never allow macroscopic material bodies to be in superpositions of macroscopically different spatial positions for any length of time that's anywhere in the ballpark of, say, our temporal discriminatory abilities or anything like that. Similarly, there's a way of by making the Gaussians not too wide, by making their width of the order of the Bohr radius or something like that, which is still a very microscopic scale, you can get the violations of energy conservation down to scales which it's plausible would never have been observed yet in experiments that we've actually done, or at least wouldn't have turned up. You know, it is compatible with sort of the data on the books. That having been said, getting hit by a wave function like this, another effect of getting hit by a wave function like this, besides, say, raising the temperature of the gas, will be to produce a higher probability than there would otherwise have been of, say, ionizations of atomic electrons in outer orbitals. Okay, it'll give them a kick. It'll give them some energy sometimes. There'll be a certain percentage of cases where it gives them enough energy to kick them out of the atom. There are, of course, all kinds of other stuff typically going on that tend to encourage ionization, jostling from nearby atoms and stuff like that. But this will add to, this ought to further increase ionization probabilities over what we would calculate from anything else. And a couple of years ago, Philip Pearl did a very careful analysis of some experiments looking for proton decay, okay, where they have an enormous amount of dense, they have a mine shaft filled with something very dense like water, okay, and the mine shaft is lined top to bottom with incredibly sensitive detectors. So the claim is you're not going to miss, there are certain kinds of subatomic events in this mine shaft full of water, not one of which you're going to miss because these detectors are so sensitive. And those numbers do put some pressure on the original version, the originally written down version of the GRW. So, yeah, it's always the case, and presumably this is the case whenever you write down a new theory, that you choose the natural constants just so stuff is going to fit into stuff that you know to be true, but it always jumps back out at you and bites you somewhere where you didn't expect. And it has other consequences, and you can go look for those consequences. So it's certainly not the case that the values of these constants are not in principle empirically available. They very much are. Yeah.
And this is just a technical point. I think I'm right. The theory of Pearl's testing is quite literally the GRW theory. The GRW theory breaks the symmetry of identical particle states. So literally speaking, it just
okay.
But there are variants of it
right.
that don't have that problem and which don't seem conceptually importantly different. So
right.
It's a heck of a lot easier to talk about the GRW theory than those variants.
Yes. And you mean what he was testing was one of those variants?
He was testing CSL.
Yeah. You think he was testing CSL?
I could be wrong about that, but I think he was testing one. I think they realised very quickly that this theory by itself wasn't literally going to be the right.
No. That's certainly true. But you can develop things that aren't. There are ways of taking care of that symmetry besides just CSL that still have hits. Right.
You could be right.
Right. Yeah.
It seems like GRW solves the measurement problem by fiat by putting it directly into dynamics.
Yeah.
So what else does it give you over decoherence aside from just assuming the more complicated?
It's not incoherent.
It solves the measurement problem.
It solves the measurement problem. Decoherence doesn't.
I'm just saying, what else besides solving the measurement problem is good?
Nothing.
Okay.
I don't know what that means. It gives you an infinite number of new physical predictions, which at the moment we have no reason to believe, besides the fact that this theory solves the measurement problem, are true. But they may turn out to be true. Then it will have given us all of those too. I mean, it's a modification of the Schrodinger equation. If you count up the number of ways in which it in principle empirically differs from the Schrodinger equation, that number is obviously infinity. So like we said, it makes these new predictions about rise in temperatures of thermally isolated systems. It makes these new predictions about ionization rates. It in principle makes an infinite number of new predictions. If you're asking, does it have original motivations other than solving the measurement problem? No, although, and maybe I'll start with this afternoon when we come back because it relates to our discussions earlier in the week. It does, if it were true, in a really interesting and I think beautiful way, reshape the foundations of statistical mechanics. So maybe we'll talk about, we're running a little late at this point, we'll talk about that when I get back. Gosh, now they're alive. Yeah.
Okay, so there are these two new fundamental constants, the rate at which you get here with the Gaussian and the width of the Gaussian.
Right.
Maybe I'm wrong about this, but the proposals you've sort of thrown out about how to measure these constants so far, it sounds like there's no good way to measure one or the other of them, measuring a combination of them. Because it seems like, with heating up gas, it'd be hard to tell the difference between being hit by narrow Gaussians infrequently or wide Gaussians frequently.
Right.
Yeah, exactly.
That's a good point. It seems to me that certainly in principle you could distinguish between, I agree with you. The two things we've mentioned so far measure a combination of those two. Because those two things, but you could, for example, as you made the Gaussian wider, okay, you're going to get to a point where the ionization, where if the Gaussian is essentially flat, okay, over lengths comparable to the diameter of an atom, there's a certain point at which the ionization probability is just going to drop to zero, even if the frequency of the collapses gets high.
I think what you're saying is technically wrong.
Really?
Yeah, Roddy said exactly that.
Oh, really?
Roddy said, look, there's certain regions that are ruled out philosophically.
Right.
Like not having experiences.
Right.
I agree with him over, over years and years.
Right.
There are other regions that are ruled out empirically.
Right.
And at least what Roddy said was that really what's tested is the product. That those empirical things just depend on the product.
And this is something Giancarlo often emphasizes. It's a certain combination of the two parameters, which is
but let's see.
empirically testable.
But probably that's right. I'm just trying to understand it better. It feels like there's a certain width, say, after which the chance of ionizing an atom is just going to drop.
With the big width, the hits are happening very quickly. So you have to really take that into account.
Right.
I don't know the details, but I think it's a fairly simple argument. How much it gives you, I'm not so sure.
Right.
Whether it rules out any discrimination whatsoever, the subtle kind, that's what you're worrying about.
Right.
But there's what it does. That special combination does have clear mathematical significance.
No, that's true. But I would be surprised if there's some sort of principled argument.
That's a good question.
That you could never discriminate between the contributions of the two. That's a good question. Yeah.
Just quick. Can you double class?
That's not a quick answer.
If it's the answer, no answer.
No, it's not. No.
What was the question?
The question is, can you make this relativistic? I would say the answer is that the results so far are encouraging.
Giancarlo and I have a paper coming out in a few months of a fully relativistic version.
Really?
Toy.
Okay, so the results are very encouraging.
Why do you mean you're worried about Roddy's theory of the interactions?
And stuff like that.
I'm talking about the original The original,
Yeah.
not Roddy's theory of flashes.
Yeah.
This is John Carl, yeah. So,
Anyway,
it's very
there's-
encouraging.
Let's put it this way, the ideas, there was a time, okay, before, that is, the breakthrough in this was a paper by Roddy Tomolka, which is now, what, 8 or 9 years old, something like that. Before that, it seems to me, lots of people, certainly me, would have bet a lot of money that the answer was no. Okay. Turns out there are ways to be clever, although there's some sense in which Bell knew this all along.
Bell was the one who really first made that observation.
Bell, so there, what happened is that Roddy picked up on some hints in an old paper of Bell's and some suggestions in an old paper of Bell's about how to begin to look at making a theory like this relativistic. That suggestion worked out really well. Ever since then, there's been a very active little industry of trying to make this relativistic. That industry is going pretty well. Yeah.
Just to parameterize that. I mean, there's two different things you might mean by can I make a relativity version. So one is, can I make a this theory which has the Poincare symmetry group, stroke gives something else in space-time, something like that. And there's a different version of the question, which is, can I come up with a theory of this kind, which is empirically adequate, not just non-relativistic quantum mechanics, but for interacting quantum field theories and for particle physics. And those are logically distinct questions. There are plenty of, you can imagine plenty of relativistic covariant theories that, for instance, don't have interactions or have long interactions. You can also imagine theories that were that empirically reproduced the predictions of the standard model, say, but which actually had some not empirically accessible violation of Poincare symmetry built into the class rule or something.
Yeah, although even which of those is going on here is a non-trivial question. It depends on preferences people have about which parts of the ontology to take seriously. And maybe we'll talk some about that.
I'm not championing that. I'm just saying that there's a logically distinct question.
Yeah, I don't know.
Probably the second's harder than the first.
I'm not sure which version the questioner had in mind, but I think David's and my answers were referring to the issue of a model which is Lorentz invariant.
Right, yeah. So that's what I want to bring up. There's two different issues.
Good. I'm sorry, we're late. Let's stop there, and we'll pick it up at